What is up, amigos? Today we have the aerodynamics of a cup of noodles, and this is chicken flavor because chicken flavor is definitely the best flavor. There are other good flavors like beef, but I think chicken just tastes better because, it's artificial. The artificialness makes it taste good. So we have the cup planes downstream, and interestingly, from the chopsticks, we do get quite a big wake, which dies out fairly quickly though. But interestingly, around the other side of the cup, we have the lip, and that impresses itself onto the wake as well, even though the cup is circular, the edge of the lip on the right side really still pops up in the wake. So that's quite interesting. And the wake does seem to die down quite quickly because even at the fifth plane, the wake has already become very unstable and it's almost sapped back up into the free stream velocity. These are the exact same planes, but they show the sub-drag, so the drag breakdown along the different planes. And interestingly, there aren't really any parts which have a lot more drag than any other parts. Like they're all fairly draggy, like they're all in the red kind of zone. And then that dies out quite quickly as we go downstream. The chopsticks, obviously, they are not good. So if you are eating your cup of noodles, consider taking the chopsticks out between fishing out noodles for yourself because that's increasing the drag of your cup. I can tell you that the drag of this cup is 0.47, the drag coefficient, which is quite draggy. Removing those chopsticks, I reckon, will drop it by about 10% perhaps. So this is now the sub-profile drag. I've calculated the profile drag for you. So this shows the pressure and the skin friction drag together. So this cup is a very bluff body, which indicates that the skin friction drag isn't going to be too much, even though we do have a little bit of serrations around the edges of the cup, like you have the indentation of the cup noodles on the side, etc. But the majority of this drag is going to be coming from the pressure drag. And we can see that because if you looked at the total drag in the last video and compare it to this profile sub drag, they look very similar. These planes, they follow a very similar outline. So this indicates that most of the total drag that we're seeing comes from the profile drag. So this Y plane is now right on the chopsticks. And I wanted to see how much of the wake is coming from the chopsticks, and a lot of it is coming from the chopsticks. So that shows us that remove those chopsticks from your cup between eating. Otherwise, you're going to be getting a very draggy cup here. But even still, without the chopsticks, the cup is still fairly draggy as well. You can see that there is quite a big wake as well, even though we are standing off the actual cup itself. This Y plane is not intersecting the cup, it's on the edge of it. So that indicates a very big wake. So for that same plane, we have the sub-drag plotted now, and the chopsticks are producing a lot of drag. Interestingly, the angle of the flow coming from the chopsticks is down, so this indicates that these chopsticks locally are producing a little bit of lift. So now we have a Y plane going straight through the cup of noodles, and the wake is really big. So first of all, at the front, the lip really makes the flow jump up and separate over the top and bottom. So that's going to make the cup very draggy to begin with. If the front was more rounded, that would make the cup more aerodynamic and would get a smaller wake. Also, the flow going into the cup is very wakey as well. It sort of recirculates around a little bit and then pops out. Also, I mentioned earlier that the chopsticks have a wake that's going down a little bit at an angle. The flow from this is going down a little bit of an angle as well, but not too much. And that is reflected in the lift coefficient. The entire lift coefficient of this object is 0.06, which is not very much, but is a little bit. And that's probably mostly from the chopsticks, I would imagine, a little bit from the cup perhaps. So this plane now is the sub-drag again. And the front lip and the bottom of the cup, they are producing a lot of drag. So we really need to round these sections at the very least, and ideally extrude the front out a little bit to make it more streamlined. The rest of the cup is also just a bluff body, so there's a lot of drag coming from everywhere, and we get this periodic fluctuation as well as we go downstream, as you'd expect. This is a Z-plane pretty close to the top of the cup, probably about 2/3 up, and the wake is huge. You can see it just blows out around the sides. Interestingly, the wake is very, it recirculates a lot. If you go downstream, maybe 2 cup diameters downstream, the flow is still moving towards the back of the cup. So it goes downstream, then recirculates back up. It's a huge recirculation zone, and then it starts to break down. And there is this periodicity to it, which we expect, and is not that crisp. That's because this cup is three-dimensional, so there are three-dimensionalities to this shedding. The sub-drag here shows, as we expect, this is a bluff body, so most of the drag is coming from a pressure differential. You have upstream, the flow is attached, downstream is separated, so you're going to get this massive low pressure downstream compared to upstream, and that's going to create this backwards force, this drag. That's why this cup is so draggy. This Z-plane is going just at the top, so just above where the noodles are inside the cup. And you can see this is a recirculation zone. It's a very low energy flow. what that indicates is probably the noodles are not going to get cooled as quickly as if you had a fast moving flow over it. So if we had a lower lip, for example, or the noodles were closer to the top of the surface, that would result in a smaller wake in this area, and your noodles would cool down a little bit quicker. Apart from that, downstream from the cup, the wake is really breaking down. It's not really two-dimensional much anymore. There's a lot of three-dimensionality to that. And you can see that because, first of all, there's not a lot of crisp periodicity to it. There's a lot of like jumbled just wake going on. And secondly, we can see that the side closest to us on like the screen is a bit bigger than the other side, and that's probably from the chopsticks. Three-dimensionality from that, as I mentioned, the wakes are coming down from the chopsticks, and that's probably interacting with this wake here. This plane shows pretty much just the chopsticks. There's a little bit of a wake from the top of the cup, and that's just from the flow that's separated from the lip. But the chopsticks are mainly isolated here, and you can see just how big the wake is just from these tiny little things. And they're even streamlined, like they're in line with each other. So I would have expected them to maybe be a little bit better, but the wake is just pretty bad from them. The sub-drag confirms just how draggy these chopsticks are. You can see that there's a huge drag just coming off of them, and this is mainly due to the pressure drag. So that's the end of this video. Make sure to like, subscribe, and if you want to get better at CFD yourself, for example, like this, so you can run other cool simulations or get better at theory, check out our courses in the link description, and I'll see you next simulation. Peace out, amigos.